Hey guys, it's Tony from Archism again, and in this video, going through our kinematic series, we're going to be deriving the constant acceleration kinematic equations. And my physics teacher in 11th grade, my junior year, liked to call these equations the cake equations. So I'm just going to refer to them as the cake equation. So moving on, let's derive our very first one. The Vf is equal to V initial plus our acceleration times our change in time. So one relationship that we have to point out here is that our acceleration is going to be equal to dv over dt. So if you haven't taken calculus, what this means is just that the acceleration, which is going to be the rate at which our velocity is increasing, is just going to be equal to this instantaneous equation right here. That d just means that at that instant, the velocity is going to be increasing at a certain rate, which is going to be equal to a. So we're going to get right into integrating this. So a times dt, you're going to multiply dt by both sides, and then you have a d term on both sides. So what this means right here is that you can use your, you can integrate on both sides because you have a d term on both sides. So right here, you're going to be integrating from t1 to t2. We're going to be integrating a, and you have your dt right there. And then on this side, you're going to be going from v initial to v final dv. So if you remember your integration rules or your antiderivative rules, you're going to use the fundamental rule of the fundamental theorem of calculus, and you're going to have this a term, and then you're going to multiply it by t, which is going to act as kind of our x here, from t1 to t2 is going to be equal to this term, our dv, and you're just going to have your v term from v initial to v final. So plugging everything in, you just have to imagine that a is kind of acts as a constant here, but it's not really. Well, a is going to be a constant because there are the constant acceleration kind of that's the equation. So acceleration is going to be constant here. So plugging this in, you're going to have through the fundamental theorem of calculus, you're just going to have a times t2 minus t1 is going to be equal to vf minus v initial. So if you look right here, our change in t term right here, that's just going to be the same as t2 minus t1 because change in t just means how much time went by over a certain period. So you're just going to have that a times that change in t is going to be equal to vf minus v initial. And our final step, just add v initial to both sides. So you're just going to have your final velocity equal to your initial velocity plus your acceleration times change in time. And there you have it, your very first cake equation derived from your acceleration, your differential acceleration equation. So moving on to the next cake equation. So right here, in order to derive this equation specifically, what you're going to do is you're going to have to remember your first cake equation. Which is, if you guys remember from the previous slide, it's just going to be v final is equal to v initial plus your acceleration times change in time. So right here, where are we going to start? You start from remembering that velocity, just like acceleration, is just going to be the rate at which the displacement of a particle or an object is increasing. So that's just going to be dx over dt. So we're going to do exactly what we did the last time. We're going to have v dt is equal to dx. But what you have to remember is that for this equation, for this cake 1 equation, you have v final. And this v final is kind of like saying that you're trying to find the velocity at a specific time. And that v initial is going to be that velocity in the past. So we're trying to find the velocity right now at a specific point. So we're going to plug in this v final into this v over here. So you're going to have your v initial plus a change in time, or we can actually just change, instead of calling it delta t, let's just call it t right now, or dt is going to be equal to dx. So just integrating this again, with our bounds being t1 to t2 again, v initial plus a times t dt going to be equal to your x initial, your x final, dx. Integrating this, just remembering the integration rules, or what we did on the last slide. Since this v initial, we know what this is going to be for sure. What we can say is this can act as kind of like a constant. So in finding the antiderivative of that is just going to be vi. I'm sorry, vi times your t term plus 1/2 a times t squared from t1 to t2. And then doing the same thing on this side, you're going to have your x term, or your position, or your displacement from the final x position, or the initial x position, to the final x position. So plugging this in for the fundamental theorem of calculus, what you're going to do is you're going to have v initial times t2 plus 1/2 a times t2 squared, minus your v initial again, but this time it's going to be t1, plus your 1/2 times acceleration times t1 squared, going to be equal to your your final position minus your initial position. And we're just going to write this, since it's kind of like a particle moving from here to here. First it was at xi, and then it went to xf. So what this is going to be, this distance right here, is just going to be change in x. So we're just going to rewrite this as change in x. Whew, almost done with this equation. So what you're going to have here then, you're going to see that there are a lot of similar terms, because you have your vi, which you know for sure. So that's going to stay the same for everything, and your 1/2 times a. So the only thing that's different is going to be your t2 and your t1. So using the property of distribution, you're just going to rewrite this as vi times t2 minus t1. So that negative sign right here just transferred over to the t1, and you left the vi as positive, and then plus 1/2 times a, and then you're going to have the same thing, t2 minus t1. Going to have that equal to change in x. So let me just move all the way up here, so I have a little bit more space. So what you're going to, just like our change in x, are from t1 to t2, that's just going to be a certain amount of time. That time is going to be equal to delta t, which just means the change over this certain time period, from 1 second to 5 seconds, from 0 seconds to 10 seconds. That's just going to be equal to your delta t term. So we're just going to rewrite t2 minus t1 as delta t. So right here, we've finished this, and you're going to have vi delta t plus 1/2. Oh, sorry, I actually forgot the squared term right here. So 1/2 times a delta t squared, which is going to be the exact same thing as you saw right here. V initial plus 1/2 a t squared. Moving on to our final cake equation. But for this one, I'm not going to use calculus. I'm actually going to just use what we found in our previous two cake equations. So I'm just going to rewrite them right here so that we don't forget them. So V final equal to V initial plus acceleration times change in time, and change in x is equal to V times change in t plus 1/2 a in t squared. So what you want to do here, you see that for you have all two of these written here. You see that what one thing that these two have in common is that they have this delta t term right here that is not contained in this third equation. So what you want to do is that you want to solve for delta t so that you can eliminate it and find this form of cake 3. So it looks like uh, finding delta t is going to be easier for cake 1. So what I'm going to do right here, I'm going to solve for it. So it's going to be Vf minus Vi equal to A change in t, and change in t right here is going to be equal to Vf minus Vi over A. So you have your delta t term right there. Let me just box this off so I'm able to use the rest of the space. So what I'm going to do now is I'm going to plug this value for delta t into my second cake equation. So you have your delta x is equal to V times Vf minus Vi over A, or sorry, it's actually going to be your Vi plus 1/2 times your A term times Vf minus V initial over A. So this time it's going to be squared. So if I want to simplify a little bit of this, I'm going to have delta x, delta x as equal to Vi times Vf minus Vi squared plus 1/2 A times Vf minus Vi over A squared. My next step is gonna, over A also. So my goal is gonna be to get rid of all these fractions. I just want to have a nice simple equation on both sides. So what I'm gonna do is I'm gonna multiply both sides by 2. You're gonna have 2 times delta x is equal to, V times Vi times Vf, minus V initial squared over A plus A times, I'm just gonna expand, find that this is gonna be equal to A squared, so this is also gonna come out of there. And if you wanna square this top part, what you're gonna have is you're gonna have ES squared minus 2. These terms are also gonna have 2's on them. So times 2 Vf Vi plus V initial squared over this A. So what you see here now, we have acceleration on the bottom for both ones, so you can add all of these terms up. So look at that. Just looking at this right now, you see that you're going to have your 2 Vi Vf positive over here, and you're going to have your 2 Vi Vf over on this side. So you're going to see that if you add them up, these two terms right here are going to cancel. And then what you see over here is that this is negative. This is a negative 2vi squared. You have a vi squared over here. So this one is also going to cancel, and this is just going to be a negative vi squared. So what you have after doing all those cancellations is just going to be 2 delta x is going to be equal to negative vi squared plus vf squared over a. So this is almost going to be done. I said I wanted to get rid of the fraction, so finally I'm going to multiply a by both sides. You're going to have 2a delta x is equal to negative vi squared plus vf squared. And to finally getting it to look like this final equation, our final step, we're just going to add vi squared to both sides. So that's just going to be vf squared plus 2a delta x. Oh, sorry. Didn't see that there. Vf squared is going to be equal to vi squared plus 2a delta x. And that looks exactly what we have up here. So there you have it, our third cake equation derived right here. So if you guys have any questions, please send it to our email right here, archismgroup@gmail.com. Thank you so much for watching all the way through. I know this was a long video, but hopefully I helped you learn how to derive these equations. As always, like, subscribe, and thank you so much for watching. I'll see you next time.